Imagine you walk into a shop selling sealed mystery boxes. The red boxes contain 4 pens each, and the blue boxes hold 5 pencils each. If you grab a handful of both and get 3 loose pens for free, you need a quick way to calculate your total haul without opening everything up. We can translate those physical items into a mathematical expression. If X represents the number of red boxes and Y is the number of blue boxes, your total item count is exactly 4X plus 5Y plus 3. Let's define the parts of what we just built. The letters X and Y represent unknown quantities, so we call them variables. The numbers attached to them, 4 and 5, are their coefficients. The standalone 3 doesn't change, so it's a constant. Finally, each distinct chunk separated by a plus sign is a term. Establishing this shared vocabulary is our very first step. With these precise definitions, we can translate complex, real-world quantities into clean, solvable formulas. This illustration shows the layout for a rectangular garden that needs to be fenced and seeded. We have a length of L meters and a width of W meters. The wire fence along the 2 lengths costs $100 per meter, giving us the term 200L. The wooden fence along the 2 widths costs $80 per meter, creating the term 160W. These calculations rely entirely on the perimeter boundary. Sowing special seeds throughout the garden costs $50 per square meter. Because seeds cover a surface, we multiply length by width to find the area. That adds 50 LW to our total cost. Translating word problems accurately requires isolating the physical reality of the situation. You have to decide if the action represents a boundary, which means adding lengths, or filling a space, which requires calculating an area. When we work with expressions containing only one variable, known as univariate polynomials, we classify them by their highest power. We do this in 3 steps: confirm there is only one variable, locate the largest exponent, and name the degree. An expression like 5y cubed plus y squared minus 8 has a highest exponent of 3, making it a cubic polynomial. An expression peaking at a squared variable is quadratic. If the highest power is exactly 1, like 3z plus 7, it is a linear polynomial. A standalone constant, like the number 8, is actually a polynomial too. We can write 8 as 8 times x to the power of 0, since anything to the 0 power is 1. Therefore, constant numbers are polynomials of degree 0. Identifying the degree immediately tells a mathematician the shape and complexity of the relationship. Today, we are focusing strictly on linear polynomials, where that degree is always 1. Polynomials act exactly like input-output machines. You feed a value into the variable, the expression processes it, and a specific result comes out the other side. Think of a chess club with a $200 joining fee plus $50 per match. The formula is 200 plus 50M. If you play 1 match, your total cost is $250. 2 matches, $300. 3 matches, $350. Notice how the cost increases by a flat $50 for every additional match. This constant, unflinching rate of change is the defining characteristic of a linear polynomial. Let's run the machine backwards. If a player paid $750 total, how many matches did they play? Pause the video and calculate the answer. Linear polynomials are highly predictable. Because the growth pattern remains perfectly constant, we can project exact outcomes infinitely into the future, or trace them backwards to find an initial input. Let's construct and solve an equation from a purely relational problem. The prompt reads, the sum of 2 numbers is 64. One number is 10 more than the other. We start by picking a base variable. Let the smaller number be x. Following the logic of the prompt, the larger number must be x plus 10. Since their sum is 64, we write the equation x plus the quantity x plus 10 equals 64. Combining like terms gives us 2x plus 10 equals 64. Subtract 10, divide by 2, and we find x equals 27. Our smaller number is 27, and adding 10 reveals the larger number is 37. By carefully assigning a variable to a base value, we can unravel complex relational statements and discover precise unknowns. Let's lock in the core rules. An algebraic expression is built from terms, which contain variables representing unknowns, coefficients multiplying those variables, and fixed constants. The degree of a univariate polynomial is determined by its highest exponent. A degree of 1 means it's linear, while a standalone constant is technically a polynomial of degree 0. Understanding linear polynomials gives us the mathematical tools to recognize constant growth patterns in the real world, frame them as predictable rules, and solve for exactly what we need.